that. And after that, he would have been fine. He could have walked around the building all day, opening doors, going up and down, not driving. But he would have been just fine. The problem is, apparently, when you take these things off, after you've really gotten used to it, then your perception takes a long time to get back to normal. So what we've been doing at this point is what I usually do when we're introducing light. And we talk about perception, because light stops being light when it hits the back of your eye, and after that it's just, who knows, right? But students seem to like that. So this came out of one of the exploratorium books. If you haven't had a chance to check the booth, they're at the very, very far end of the booth, Exploratorium in San Francisco. They got some of the best books with demos, activities, all kinds of really neat stuff in there. So, check that out. What else? All right. I've got a glass rod here. Is it transparent? Answer begins with a Y. Yes. Good. It is Saturday morning, isn't it? Right? Is it invisible? No. What's the difference? What would have to happen for this to be invisible and not just transparent? Yeah. The reason that we can see this, there's a couple of things going on. Light reflects off the surface, so it's changing its path because of that. But more importantly, light refracts as it goes through this cylindrical shape and changes its path. And so light coming from the back of the room doesn't go straight through it, it's bent. So this is changing the path of the light, and we can see where that happens. So in order to be really invisible, we'd have to put this into some sort of a medium where the light travels at exactly the same speed in that medium as it enters the Pyrex rod and comes out the other side, so the light doesn't even notice that it's gone from the medium into the rod and out the other side. Turns out that if this is Pyrex, which it is, and we've got that very, very exotic, expensive, and highly sought after liquid, which has exactly the same refractive index as Pyrex, turns out to be vegetable oil. The speed of light in the oil and the speed of light in the Pyrex rod are exactly the same. So when we put the rod into the oil, it's there. You can't see. So that's cheap and quick. Now, make sure it's Pyrex. Thing to do is to go into the chemistry storage area, because they're probably still busy doing significant figures anyway.
Oh man.
And go through, take a bottle of oil in with you and just go through all the stirring rods until you find one for it. Speaking of significant figures, anybody here ever been to the Smithsonian in Washington, D.C.? Yeah, they see the dinosaurs. Isn't that cool? We were there a number of years ago when our girls were younger, and the guy that was showing us around, young fellow, very good, very knowledgeable, and we got to one particular thing, and he said, well, these remains are 98,000,004 years old. And I said, wow. How do your research people manage to date these things so precisely? He said, I have no idea, sir. All I can tell you is that when I started working here 4 years ago, okay. Phosphorescence, not quite the same as when you fluorescence, right? Fluorescence is real time. The light falls on, the UV hits the material, the light turns off right away. Phosphorescence is kind of a time delay. And we can show that quite nicely. I've got some of this glow paper up here. You go to a craft shop, especially around Halloween, they sell it, and it's the phosphor-coated paper. You can cut it up and make little stars and stick them on the wall or decorate your hat or whatever. And a couple of sheets of this, And we need a light source to activate it, because what phosphorescence is doing is taking the visible light, which hits it, and re-emitting it over a period of seconds, 10, 20 seconds, whatever. And you actually buy the phosphor paint, but this is much easier to work with. So we're going to use a light source here, which is one of these, remember these things? Yeah, they're all disposable cameras. You need one with a flash unit, or you could get, just use a camera with a flash. But these are free, which appeals to my heritage from Yorkshire. You see, a Yorkshireman is like a Scotsman who's been stripped of his generosities. The other definition of a Yorkshireman is that he's often wrong, but he's never in doubt. Now, in order to activate the flash, you need to be able to take a picture, of course, and remember how you changed with the film cartridge in there, you'd roll it onto the next frame. Well, of course, without a film there, there's nothing to pull this little blue sprocket, so you just do it by hand. And then you just take a picture, right? Do we see that?
Anybody with epilepsy?
Are we awake yet?
Why?
Good. So, here's our light source, and I'm going to need someone with a steady hand. Do you have a steady hand, sir?
I do.
Excellent. Can you come up and provide a steady hand? What's your name?
Patrick.
Patrick. Nice to meet you, Patrick. Okay, you're going to put your hand in front of the glow sheets, just right up against it. Perfect. There we go. Take your hand away, please. Nothing happened because it's way too bright in here. So we're going to have to do it again. Can somebody hit the lights? Do we have a light switch? Check. It's in the back of the room. Back of the room. Oh, there's nobody back there. Let's try that again. Let's wind this up again. Here we go. There's Patrick's hand. There's Patrick's hand. Shut up. There we go. Could we have the lights again, please? Now, that was when your hand was stationary. What I want you to do is to get pretty close up here, and then wave your hand as quickly as you can in front of it. We'll see. Again, could we have the lights, please, while Patrick's waving? Faster. Better. Thank you. Yeah, thanks. Thanks very much, Pat. Oh, come give the lights, please. He's going to stumble. And then his lawyer's going to be on to me in a minute. This is a fairly small, short flash duration. The other neat thing about these is that you've got to be really careful when it's charged up, because there's a pretty good size capacitor in it. All of the circuitry here is to take the 1.5 volt cell and boost it up to the 400 or so volts which is needed to activate the flash. Part of that process is this black cylinder under here, which is the capacitor. So that's storing up all of that energy at high voltage, ready to dump it all at once and activate the flash. But if you happen to touch the terminals of it, you get a little bit of a shock. So the idea in general is to leave this thing charged up in the storage cupboard so that your teaching colleague, when he's doing the demo next time, not that I want to give you any ideas or anything. Now, which part of the spectrum is actually activating the phosphorescence? Let's take a look at that. We've got a little old red laser here, and see if that does anything. Nah. We've got a green laser. Comes way more, but doesn't seem to do anything to the phosphorescence. I got a blue LED here. Can we just kill the lights for a second, please? That's great. Let's try the blue LED. We're getting a little bit, getting something. But now, what we really need is to go to a higher energy photon, which is ultraviolet. There we go. So it's the higher energy. Thank you. Can you do the lights for me? Thank you. The higher energy, higher frequency photons that are activating the phosphorescence. You don't need to go out and buy the new UV lasers. What you do is to go to a toy store and get the secret writing kits. which contains 2 of these little UV lights, so that you can send each other messages. This is kind of like low-tech texting. Or maybe Aztec texting. One of my colleagues who retired a number of years ago, he worked for a while after teaching as a consultant for a company that made coatings. And actually, he was a really neat guy. When he first retired, his wife said, "Well, Gordon, you need a project. You got to be, otherwise you're going to be under my feet." He said, "Yeah, I'll think of something." So anyway, eventually he came up with a project that he said, "Well, I'm going to take advantage of my background in chemical engineering. So my retirement project is to take large quantities of beer and wine and smaller quantities of single malt scotch and gradually convert them into urine." His wife was thrilled. "Oh, thank God you got something to do."
I love it.
In his part-time work at the coatings company, they came up with, by accident, as many of these things do, a glue. It's not on the market yet, but he gave me a small sample here. And this is a very, very interesting glue. It's odorless, colorless, as you can see, but it's got a couple of very interesting characteristics. It's particularly effective on styrofoam. So what we've got is, I finally found a place in downtown Indianapolis where I could buy groceries. And I got a dozen eggs in a styrofoam container. And we're going to put a little bit of this. You don't need a lot of this stuff. This is really very interesting stuff here. We're going to put a little bit under this end of the egg carton and see if we can get this to glue onto there. So, a couple of things about this adhesive. You know those Post-it notes that you can pick up and stick down in another? Guess what? The other thing is that, like some of these super glues, they're like a skin cement. You've got to really be careful with it. This stuff, it's not an issue. It doesn't affect skin at all. In fact, the chemical formula is HIJKLMNO, or H2O. And of course, these are not just a regular box of eggs. What we've got is 12 empty eggshells, but the 2 at this end have got 200-gram masses underneath them. So it's going to balance anywhere, right? You're an egghead, aren't you?
Not the first time I've been called that.
Now, why on earth would I confuse my students like that? Well, first of all, because I can. But secondly, because later on when we're talking about center of mass, instead of always assuming that the center of mass is in the geometric center of the body, I say, well, remember the eggs? Yeah. So if you want to find the center of mass of something like this, then the easiest way to do it is just to slide your fingers together underneath it, keeping it level, and it will automatically center at the center of mass. You could even keep one finger stationary and slide with the other. I'm moving my left hand, leaving my right hand stationary, and it's still going to do the same thing. So check your neighbors, see if you can figure out what's going on.
Force of friction. Right? Static versus kinetic friction.
Whichever side is heavier is going to press down more.
Yeah. Yeah. Kinetic versus static friction.
Right.
It's the difference in the coefficients of friction. He teaches like Hewitt. Got a couple of Hewitt's mannerisms, you know. He does the starts with letter Y. That's a Hewitt thing. Starts with this letter. That's a Hewitt thing, and then check your neighbor. That's a Hewitt thing.
Okay, folks. There's two kinds of coefficients of friction up there. There's a static and there's a kinetic or sliding friction. Which is usually greater? Static friction, that's right. So when the stick is not moving, that's a result of static friction. When the stick is sliding, then there's kinetic, sliding friction going on. Now, if we start to push our fingers together, because of the relative amount of the weight that's acting against each finger, then there's a little bit more of a normal force in one than there is in the other. And so we're going to find one point where this force here and this force here, as we push our fingers together, it's going to be a combination of static on one and kinetic on the other, and they're going to meet quite nicely in the middle. Try it yourself with a pencil or a pen. Just slide them together. Now, we're back to significant digits again, aren't we, right? It doesn't have to be one of these organic, disgusting, sweating things here. You could actually do it with a very smooth thing like a pen. And if you want to keep the pen stationary and slide my finger, then you think, well, of course, but what's happening to the amount of weight that's on my finger as we put more and more of this stick over the other side? It's getting less and less and less, so the friction force is reducing. So it's still going to work. And it doesn't even need to be a uniform thing like a meter stick. This is, by the way, you know, the 50 best demos to do before you die that will fit in a suitcase. Because otherwise the guys at Homeland Security, when I was coming in through customs, would have nothing to do all day. Try with a golf club. This is my little mini putter here. Well, the center of mass of this is not in the geometric center, right? This is like our box of eggs. More weight at one side than the other, but it doesn't matter. Nature will take care of it, so we always meet at the center. So if you've got an old golf club kicking around in your basement, take it to school and use it for a center of mass. Okay. How many people here have used any of Paul Hewitt's conceptual physics materials? Good. If you've never heard of Paul Hewitt, you should take the time to run down to the exhibit hall and look at the big Pearson exhibit. Just as you go in through the entrance, Pearson has staked out the high ground there. And look for Paul Hewitt's conceptual physics, particularly the high school edition. It's 4th edition now. If you've not used any of that stuff, I would really strongly recommend it. One of his things is that equations should be thought of in terms of a guide to thinking. For example, if we take the so-called wave equation, which we think of usually as being written as the speed of the wave is equal to the frequency of the wave times the wavelength. That's a familiar expression. However, many of my students, when asked, what does the speed of a wave depend on? What do you think they answered? Frequency times wavelength. What does the speed of a wave depend on? Yeah, it's the kind of wave it is in the medium through which it's passing. That's what determines the speed of the wave. So rather than thinking of this equation as this depends on this, which form of the equation would be more conceptually compelling in terms of this depends on this stuff? If we rearrange it, the math teachers would say, well, nothing's changed. But you physics types might want to think of this equation in one other way. Which of those do you think is close to being the one that says this thing on the left depends on those things on the right? Check your neighbors, see what they think.
The last one.
Solving for V, solving for F, solving for...
Because you have no control over V, and you have no control over frequency.
Yeah, frequency doesn't change and velocity doesn't change in the same medium, right?
The frequency is whatever the frequency that's causing the waves.
Yeah.
You know, whatever's
Yeah, so
oscillating.
you can't change that. And as it travels into a new medium, the speed may change, but the frequency doesn't. And the speed changing is what affects the wavelength, not the frequency. Yeah, I would agree.
Let me ask you this question. We said that the speed depends on the medium and the type of wave that it is. What does the frequency depend on? What determines the frequency of a wave? It starts with an F and it ends with frequency of the source. Isn't that right? The frequency of the source determines the frequency of the wave. So it doesn't depend on speed and wavelength. It only depends on what the source was. So which of these three then is the one that actually states this equation in terms of what something depends on?
The last one?
The wavelength, that's right, the last one. So when we're introducing and getting to know this equation, sorry? Oh, I see, I'm sorry, yeah. If we think of this as speed depends on these things, no, speed depends on the kind of wave, what's the medium? Think of this as, oh, frequency depends on, no, frequency depends on the frequency of the source. That's what determines it. So this is a better way to think of this equation because it's the wavelength which is determined by speed and frequency.
Are you saying that wavelength and frequency are different things?
Oh yes.
Why?
Because the frequency is determined, predetermined at the source. It will not change as the wave proceeds. The wavelength will change depending on what happens over here. Let me show you. If we take an example, let's say we've got a glass of water here. Correct. Correct. Let's think of this jug of water and our laser beam. If we shoot this laser beam from the air into the water, we've got three things to consider: speed, frequency, and wavelength. As that beam of light goes from air to water, ask your neighbor, what happens to the speed, what happens to the frequency, and what happens to the
It
wavelength?
goes down.
Okay?
Wavelength goes down.
Going from
Frequency
air
stays the same.
into water.
I actually wasn't paying attention.
Oh.
I was looking at my slide.
Yeah.
What was the question?
The question is, what's the only thing that changes as it enters the water? The green laser.
Oh,
The
yeah.
only thing that changes is the speed and the wavelength, right?
Yes, the frequency does not
Frequency
change.
changes, right.
Right.
divided by the frequency in air. But since frequency isn't going to change, the wavelength in water is going to be a function of what over what? Speed in water divided by the frequency. And the frequency is still the same. Frequency hasn't changed. So the speed in water is less, so that's a smaller amount, over the same frequency. So what does that tell us about the wavelength in the water? Is it going to be the same as it was in air? No. Will it be longer or shorter? Check your neighbors. I'm going to be a little wave here. And I'm going to have a certain frequency. And I'm going to have a certain speed. And as I'm being a wave in air until I get to here. This is when I pass into the water. Right? So I'm a wave, I've got a fixed frequency. This source behind me has determined my frequency. So here's my frequency. Can't change. And I've got a certain speed in the air. Here I go, moving through the air. What happens at this point? I have to slow down, but I can't change my frequency. So what's going to have to happen? Help me out here. What do I need to do? That's right. I've got to take smaller steps. So I'm moving slower, but with the same frequency. And if I turn around and I go back, guess what? It reverses. So the wavelength goes down because the speed has changed and the frequency stays the same. So that's the way to think about the wave equation. If you can do it, if you can get your students on side, that's great. What about Newton's second law of motion? That's exactly it. We usually write it as force, net force is mass times acceleration.
Right.
The way I would do it.
Yeah.
You know, to introduce it.
So we're all familiar with
Every
this.
which way.
But most of the time, the way that we're using this is in the form of how much acceleration do we get depending on the amount of net force that's causing the acceleration divided by the mass. So this, again, I would argue, is a better way to think of the equation. That's the only way to think of the equation.
That's the way Newton wrote it.
That's apparently the way that Newton wrote it, yeah. But he wrote it much more neatly than I did. But it wasn't Newton's wrote. Now, one of the interesting things that happens with acceleration, our students don't know, they don't have a feeling for acceleration. We've all grown up with a speedometer in the car. Come on, Dad, come on, you go a little faster. But we don't have an accelerometer in the car, which is a pity, but most of the time it would be pretty boring when you're on the highway at cruise control, because what's your accelerometer going to say? But students haven't grown up with acceleration. And we all know that when we think of saying, okay, you take an object and you launch it into the air upwards, at the very top of the path, what's the speed going to be? Zero. What's the acceleration going to be? What are your students going to think?
Zero.
Of course. It's not moving. How can it be accelerating, dummy? He said, okay, well, you know, fair enough. How can we figure this out? What we need is a device which tells us when something is accelerating under the effect of gravity. And that's what we have here. We've got a Coke bottle, and there's a little hole in the bottom. I just poked a hole in the bottom there. And we're going to fill this with water. And this is going to be our free fall detector. So here's our free fall detector being got ready. Now, I know that some of you, your budget won't run to this stuff, but you know, I figured I'd show it to you anyway. table in my classroom. I don't trust these tables, so I'm just going to do it on a sort of smaller scale. Now, the water doesn't come out yet, because why not?
You got the cap on.
Yeah, I got the cap on there, so if the water had to come out, some air would have to get in. That's not going to happen. So as soon as we release and crack that lock there, then we've got gravity. You okay with that, Connor? Correct response. So, we've got gravity up here too. Let's check. There we go. Now, that water comes down and it's being pulled down by what? Starts with a G. Gravity. How come the bottle doesn't fall down as well? Starts with an H. Hopkinson. I'm holding it, right? So as long as I hold the bottle, then we see the water coming out. What would happen, do you think, if I let go of this and the whole thing was allowed to fall down? Will the water fall faster than the bottle? Will the bottle fall faster than the water? Or will they fall together? Same gravity. Yeah, gravity never sleeps. Same for everything. So when we let go of this thing and let it drop into the garbage can, what should we expect?
No water leaks.
The water should not be leaking out, okay? Now let's just check, make sure we still got gravity. Yep, we do. Okay, 1, 2, 3, go. Now, over a longer period, and with your students' cell phone cameras activated, you can confirm that the water was not spilling out during free fall. Okay. So the next question is, what would happen if we were to launch the bottle vertically upwards on the way up after it leaves my hands?
Oh, this is going to be fun.
What's going to happen in its trajectory up? We know what happens on the way down, we just watched that. But what's going to happen on the way up after it leaves my hand and gets to the very top before it turns around and comes down? Check your data, please, and see if you can predict.
Not going to leak.
It's not going to leak.
Thanks. And he's really got a high ceiling here. So,
Now, wait a minute. Wait a minute. Shouldn't it leak on the way up?
It's a free fall.
But as he exerts a force on it, shouldn't it?
Well, during the launch, once accelerating.
It's actually gonna push more than it normally would because he's got more than one G, right?
But as soon as it leaves his hand,
Right, then
it's
it'll
going to
stop.
be, it's
But
like
if
the Mama Comet.
Yeah.
And half the time you're in 0 G on the Mama Comet is you're actually climbing.
Yeah.
It's not the downward
It's
part.
actually the whole arc of the parabola. Yeah.
Should we try?
You got nice tall ceilings here.
Make sure to throw it real hard.
It's a bit of a challenge, isn't it? Yeah. Okay, we got good gravity here. Okay, ready? On 3. 1, 2, 3. What happened on the way up? Nothing. How come? After it left my hands, what's the only force acting on it? It starts with a G. Gravity. You mean it's in free fall while it's going up? Is it too late to change courses? That's right, it's in free fall all the time after it's left the launch pad. The only thing that's driving it is gravity. So we've got our free fall detector here. If the water is not coming out of the bottle, it's in free fall. Or my thumb's over the opening. Anybody here ever played a game called baseball? You're getting leery, aren't you? You know? I'm looking for a catcher. Blue shirt. What's your name, sir? Bennett. Bennett? Bennett, you're going to be the catcher.
Sorry, I've been volunteering years.
It's a team of sport, right? So we've got a projectile here. And we're going to launch the projectile, and Bennett's going to catch it. And as soon as he catches it, he's going to try to stop it leaking all over the place, right? But again, I'll try to keep it in that upward orientation throughout the passage. Because students think that something's going on to a projectile other than just being pulled down by gravity. But if this thing is in free fall, what should happen as it arcs through the air towards Bennett? Nothing. Okay, let's make sure we got gravity. Yeah, we do. Okay, 1, 2, 3. The question came up, why didn't we allow some of the water, why didn't we drop it originally? Why wasn't it leaking when we let it drop? Why don't we do that, right? Let's see what's going to happen now. We don't care what happens to the bottom. So instead of just saying 1, 2, 3 and dropping it, we're going to start it spouting that way. And then see what happens to the flow of water as it falls. This is going to be fairly quick, so let's see if we got gravity. We do. 1, 2, 3. There you go. Perfect, thank you. I love water. It's not my classroom, so what? Even better. Okay. Circular motion, that's acceleration, isn't it? Do we still teach radians to kids? Or in math class, whatever? Students sometimes have a tough time with radians. I'm not too sure why, but this helps. You get 3 rulers, 3 12-inch rulers, and we make a triangle. This is what kind of a triangle? Starts with an equi, ends with a lateral. Help me out, you guys. I know it's Saturday morning, but come on. So we've got an equilateral triangle. What's the number of degrees in each corner? Starts with a 6.
60.
60. Very good. If we had a bicycle wheel with a radius of 12 inches, you know, like the ones with the handles on, and you did it. Any of you got those in your prep room somewhere or storage room? Okay.
Yep.
Pull that out when you're talking about radians and have this handy. Because you ask your students, you say, okay, here's this wheel. How many of these triangles would it take to go all the way around the wheel, one complete turn? Check your neighbors, see how many you're going to need.
6.
Somewhere between 5 and 7, isn't it? All right.
6.5.
So you're going to take 6 of these guys, right? 6 of these will fit in that circle. Now, what happens now if we curve out one side of the triangle to be part of a circle? We now have a 12-inch arc and a 12-inch radius. But what's happened to that 60 degrees down in this corner when we do that? Does it stay 60? Does it get bigger? No, it gets a little bit smaller. It's a little bit less than 60, isn't it? In fact, it's actually 1 radian. That's how we define a radian, with an arc length which is equal to the radius of the angle. Now, let's ask the question again with our bicycle wheel. How many of these will it take to go all the way around that circle? Is it still going to be exactly 6? It's going to be a little bit more than 6. About 2 pi radians in one full circle, right? There you go. 2 pi radians. There they are. So that's a nice little visual of the radian.
That's wonderful.
What about Ohm's 3 laws?
3 laws.
We know Ohm's 3 laws, don't we? Apparently, Ohm had a very miserable personal life. It's true. He was fairly tormented about various things. And when he died, on his tombstone, he had written in Latin, Tandem Felix, happy at last. So here's Ohm Ohm's three laws. So you're all making notes about this, I hope, right? We normally think of it in this form. But at the very, very introductory level, somewhere in middle school or junior high, when you first start using Ohm's law, the voltage is probably preset. It's going to be a 6-volt battery or a 1-volt, 1.5-volt cell. Right? This form, mathematically identical, but resistance doesn't depend on voltage and current. It can be defined in units of voltage and current, but the resistance is determined by the kind of material it is and the dimensions, the temperature, etc. So that's what determines the resistance. So I would argue that the third form, where current is determined by voltage applied and the resistance to which it's applied, is a more useful way to introduce this concept. So here's a question for you. Can you have a good-sized voltage without having a good-sized current? Sure you can. We've all seen a Van de Graaff generator, right? Hundreds of thousands of volts, but hardly any current. The Van de Graaff generator was developed by Dr. Edward Generator. Let's turn the question around. Can you have a good-sized current without having a big voltage? Check your neighbors, see what they say.
Small resistance.
Sure. I think you can have a really small resistance.
Superconductor.
Yep.
You're done?
Is that possible? Can you have a good-sized current without having a huge voltage? What does current depend on? Voltage and resistance. So, if we have a reasonable voltage, but we've got a tiny, tiny little resistance, then guess what? We get a good-sized current. So if you take a 9-volt battery, fairly modest,
Drawing the equation anyway.
and some steel wool, and you just touch it across the terminals. Sure. So when you go out to buy a new 9-volt battery, you don't just throw it in the pocket where you keep your change, right? Make sure those are in separate bags before they go in the suitcase. Okay. Static electricity, you all do races, right? Races! Balloons! Pop cans. Dear. So when you rub the balloon against your hair, and then you put the pop can on the table, and you get it going. So all you need is a class set of pop cans. I told you there's going to be a big budget problem here as soon as you get back. And a bunch of balloons, and just give them to the kids, and all hell breaks loose. It's great. Because they'll soon organize races up and down the tables over tug of war. You get 2 teams with tug of war. You get the idea. So when you rub the balloon on your hair, the balloon picks up one kind of charge. What happened to your hair? It's left with the opposite. So what positives and negatives, they what, attract or repel? They attract. So the positive and the negative should attract, right? Do they? My wife told me I had a magnetic personality. I budget again. Dig deep, Gary. I am. Oh, Penny, look at that.
Yeah, he
Hang
wins.
tight. Ah. And what we got here is a digital multimeter. These used to be in the old days considered very expensive, but now they're what, $10 at Radio Shack or something?
Get them for $6 online.
3 at Harbor
We're
Freight
going to go down
Yeah.
when they're unsafe.
on the DC voltage side to a low range. We're on 2,000 millivolts here, up to 2,000 millivolts. When I lived in Turkey, my buddy's truck was always being ripped out. The battery was being ripped off out of the hood. So eventually he put a sign on it, danger, 12,000 millivolts. No way, man. So here's our, I don't have a display version of one of these. I'm sure they're out there somewhere, but I don't know. Anyway, so you're going to be my meter reader. You're going to be the meter reader? You get a chair. Look at this. Okay, you get a, okay, what's your name?
Brandon.
Brandon. Brandon or Brendan?
Brandon.
Brandon, good name, thank you. Okay, Brandon, we're going to put the penny on there, and we're going to put the pop can on here, and you're going to be my electrolyte, as it were. So what I'd like you to do, your name is? Rachel. Rachel. Rachel, if you'd like to hold the penny in one hand, and pop can in the other hand. Anything happening? Okay, what are we up to so far?
101.
101 millivolts. Okay, now if you change your grip on this, because the paint is an insulator, so if you can hold your hand around the base there, get a lot more contact on the aluminum.
450.
450. Now, if we could spring for the expense of one more connecting cord and another pop can and maybe another penny, we might be able to make 2 cells in series. Because you're a cell right now, right? Do you have a cell phone? Okay. Now you know why. Yeah. Okay, now you can do this. You can get the kids to do it. Different coins. They'll find all kinds of different metals to try it with. If you've got a class set of multimeters, there's your beginning for circuits, right? So instead of finding it, then conducting, because the paint's on here. Oh, why does it work if I hold it here as well as if I hold it down here? Now, we're going to modify this slightly. We're going to take the penny out of there. Thank you, sir. Appreciate it. And we're gonna go from Aztec to low-tech. So you go down to the hardware store, you get some 1/2-inch copper pipe. So you're gonna hold that in one hand.
It's pretty expensive.
You also pick up some steel conduit for electrical lines, which is zinc coated. So we've now got zinc and copper. So let's see what we've got now. 820 millivolts. Okay. Part of the battery, because now we're going to have 2 cells in series. What's your name? Jenny. Okay, Jenny. What I'm going to do is to give Jenny this zinc with her left hand, and this copper with her right hand. And I'm going to give Rachel this zinc, and we're going to join your zinc to your copper. And what do we expect to happen?
1.6 volts.
Well, unless Jenny's clinically dead, yes, I hope so. 1.6 volts. Now we have a battery. When you go into the store and you see the display and it says 1.5 volt batteries, doesn't it drive you nuts? What should they be selling?
Cells.
1.5 volt cells. It's only a battery if you've got multiple cells in series. So part of your homework when you get home is to take a big marker to the drugstore, cross out the words batteries and write in cells, damn it. Now, when you buy this piece of conduit or this piece of copper pipe, you can make a class set of these things. And you can actually graph the voltage against the number of students, and it's a dead straight line. You can do it with aluminum tubes and copper, or aluminum and zinc, and graph it. You can do a lot of stuff with this. you can put them in parallel, because when you start cutting up this class set of short ones, leave one piece about 3 or 4 feet long, and then you can get a little train of 3 or 4 students in there in parallel with the one connection too. And you don't get the added voltages then, because it's really one cell, it's just a bigger kind of cell. Right? Thank you very much. You are electrifying. We've got 2 minutes left. Which one to do? Let's have a look. Did that. Yeah, sure.
With that battery, you have 1.5 volts.
I'm sorry?
You have 1.5, 1.6 volts with that human battery you just made.
Yeah.
Did you replace the multimeter with a small little like maglite flashlight that runs on 1.5 volt battery?
The problem is the current that we're getting is very, very small because charming as our cells were, they've got huge internal resistances. So it's a nice voltage generator, but the current is not going to be there. So maybe with enough kids and a very small LED, I don't know, I haven't tried that. But certainly nothing more than that, I don't think. Okay, let's do one last more. Yes? We've got time for this. You've all got some of these, right? Whirly tubes. Do you have one of these? Stretchy tube. Very handy if you're riding on the bus or the train and there's some jackass next to you yakking away on the cell phone. Just pull it out. Excuse me, I'm trying to have a conversation. Excuse me, I'm doing physics. So, it's the idea is that when this is short, a small body of air, small column of air, a higher frequency, the longer it gets, the more mass has to vibrate, so the frequency goes down. All right. Okay, so if we do a steady tone, here's an identical tube except that I chopped about 3 or 4 inches off the top. So when we do the same thing with this one, will we hear the same note? Higher or lower? Check your neighbors. Higher or lower?
Higher. It's a shorter tube.
Except with those, it depends on how fast you whirl it because there's a series of harmonics.
But if you roll them both at the same time.
With the same speed, then the shorter one should be higher.
Yeah.
Is it higher or lower?
Higher.
Let's try it. Here's the original one. A little higher? Slightly higher. It's a smaller body of air. Slightly higher. Now, which way is the air moving through the tube to generate that sound? Is it coming in the bottom, out the top, or in the top, out the bottom? Check your neighbor, please.
In the bottom, out the top.
Yeah.
Moving in, lower pressure.
Yeah.
I'm wondering, can you do both
Now
at the
wait a
same
minute.
time and
Wait
get
a minute.
beats?
Wait a minute. Because isn't the end that's moving fastest, according to Bernoulli's principle, having lower pressure?
That's what I'm saying. And therefore, it's going to enter at the bottom and go out. It's going to go in the high pressure, out the low pressure.
Hey, folks!
Why would it go in the high pressure? Wouldn't it go in the
I'm going to do a
low
little
pressure?
experiment, just to wrap up here. In order to figure out which way the air is moving, whether it's coming in the top, out the bottom, or in the bottom, out the top, we're going to take some confetti. If you go to the photocopy machine at school and you look in the 3-hole punch, bingo.